Theodore Belecciu, and I will be doing a 3-minute paper presentation on the paper titled at the top of this slide. So the authors begin by noting that in aggregate, commonly used software for protein ligand docking like AutoDock, Glide, and FlexX, and Rosetta have similar performances across all types of proteins, broadly speaking. However, Rosetta is significantly slower than the others, making it way less feasible for screening of large ligand libraries against proteins. And they hypothesize that this is because of the inefficiency of the standard two-stage Rosetta ligand docking process. And the standard docking process they describe consists of two main steps, the translate and rotate step. In the translate step, the ligand undergoes up to 50 random translations within 5 angstroms of a user-specified starting position. And this step ends only once the ligand experiences attraction or neither attraction nor repulsion, a neutral state. And then the rotation step happens only once the translation step terminates under the old protocol. And the ligand undergoes up to 500 random rotations of varying magnitude, and a set of favorable orientations are generated that eliminate any repulsion and maximize attraction to the protein. And lastly, all atom positions in the entire protein-ligand interface are minimized and final models are generated. And the authors hypothesized that the fact that the translate and rotate steps are separate make it so that Rosetta misses out entirely on many favorable initial ligand positions. They give the example of a rod-shaped ligand going into a hypothetical rod-shaped protein pocket. And under the current protocol, if the ligand is oriented incorrectly to begin with before any of the stages and is translated to a favorable or neutral position, it's way less likely that it will actually enter the pocket properly oriented as it should. So they decide to combine the translate and rotate steps into one single step that they name the transform step. So both processes happen simultaneously in that step. And they tested this on a set of experimentally determined protein ligand structures, crystal structures. And they determined that under the old protocol, the amount of time needed to generate a model was 49 seconds, and under the new one, only 9.3 seconds. That's quite a significant difference. And it gets even better. The new protocol samples models with an RMSD to the experimental structure of less than 2 angstroms 7% of the time, while the old one only does so 0.16% of the time. So the docking success rate and quality improved significantly. And the authors conclude that this makes RosettaLigand feasible for virtual high-throughput screening. Really, for the first time, it really sucked before this in terms of computational load and inefficiency. And the total processing time per ligand was reduced from several hours to 15 minutes.